Okay. Hello. Okay, I think it's time to start. So yeah, the midterm is still grading, and so hopefully you can finish grading on Wednesday, and we'll talk more about what everyone get wrong. Since people are not, from what I heard, people are not too familiar with the proofs, so maybe we'll go over the proof questions more carefully on Wednesday. Okay. But for now, we are in chapter 4, and so this is a new topic. We are talking about linear transform and the linear operators. So, yeah, let's go to the start. Yeah, so linear transform, once again, we are talking about mapping from a vector space to another vector space. And if the mapping respects the linear combination of the vector space, then it's called a linear transformation. So if you have some linear combination from the starting space V, and you will get mapped to the same linear combination, so same set of coefficient alpha and beta, then this is called linear transformation. And we see that you can either define linear transformation in this way, so any linear combination alpha and beta, or you can break this into two smaller rules. So you can also say if you preserve this vector addition, so you have any two vector addition maybe to addition of two vectors, and you also respect the scalar multiplication. So scalar multiplication on the starting space mapped to the scalar multiplication of n space. Yeah, so you can either have this big rule or break into two small rules that are equivalent. Okay. And we have another name. So if our starting space and the end space are the same, is a little spatial. So it's like you are doing something on this space V itself, then we call it a linear operator. So you transform something on V to another thing on V. And so now we see example of a linear transformation or linear operation. So this, you stretch everything 3 times is a linear operation. You have a linear combination, then the combination got stretched 3 times. You can either do combination first, or you can do the stretch 3 times first. Okay. And also we have seen that projection is a linear operation. So if you have a vector 2 dimension and you project it down to the x-axis, then this is a linear operation. And also reflection is a linear operation. So you negate your y value and you reflect around this x-axis, then this is a linear operation. Also rotation is a linear operation. So you rotate every vector on this 2D dimensional plane 90 degrees. And yeah, this is linear. Okay. And we have more example. Okay. then we have an example of this calculating the length of your vector is not linear. Because you get a negative sign on it, then your length is still not changing. So if you multiply this by alpha equals -1, then length doesn't change, but you should get a negative value. So this is not a linear transformation. Okay. And so something we'll see more today is you can write linear combination as a matrix A. Okay. So here we do another directional proof. So we say from Rn to Rn, then you can always define a linear operation by this A. So you just say whatever vector on Rn you multiply by A, and it becomes a vector on Rn. And you can easily check that this is linear, just because, well, matrix multiplication has those very linear rules we have been talking about. So yeah, so matrix multiplication has these distributive rules and the associative rule that make it respect the linear combination of the input, and it becomes linear combination of the output. And I guess it is a little circular But this is also why we call those rules are very linear, because they respect the linear operations, linear transforms. So because they are like linear transforms. And anyway, so as we will see today, every transform from Rn to Rn can be defined by a matrix, and actually any linear transformation can be associated with a matrix. Okay. But now back to 4.1 for now. We're seeing some property of a linear transformation. So if it's linear, you should map 0 to 0, and you should map this minus v to minus of what is minus L of v. Okay. And also this linear combination. So in the definition, we only have two of them here, but actually it's easy to seem true that you linear transform any number of linear combination, and you get a linear combination of the output. Okay. And then we see this two concepts of image and a kernel that's related to linear transformation. So you have a linear transformation, then you can define this kernel, and it's a subspace, and it's everything that maps to 0. Okay. So this is a linear space, and we know 0 will map 0, but we know 0 will map 0, but sometimes more than one thing is mapped to 0. Then those will be called kernel. And with image, and it means you take whatever subspace in your V, and you will map to its image L of S. And so when this S is everything in V, then you get another special name. It's called a range of L. So it's everything possible, everything that can be reached by mapping something with L. Yeah. Okay. And we have our theorem saying that the kernel and the range. The kernel is a subspace, and the image of every subspace is a subspace. And the proof is pretty straightforward. You check the definition, and you see that things inside kernel has closure under addition and scalar multiplication, and things under image, things in the image has closure under scalar multiplication and addition. So they are subspaces. Okay, so that's a review of this time. Any question? If not, yeah, then let's go slowly through the examples to give you more idea about, or more feeling about what are kernel and the image. Okay, so kernel. So first we define our linear transformation. It's a linear transformation from R2 to R2. It's very easy to visualize. And what we already see is projection. So your linear operation is you keep your x1 and you throw out the second coordinate. So it's a projection. And so what's kernel? And the kernel is everything that will map to 0. Okay. So you want, after you do this linear, you do this projection, it becomes 0. And okay, so maybe it's good to draw a picture here. Okay. So projection on 2D look like this, right? So projection on 2D, so you have whatever vector here, and it will get projected here. And we say kernel is whatever thing are the things that will get mapped to 0. Okay. And so kernel is then the kernel will be the y-axis here. So this is kernel of L. Because everything on y-axis you can you project onto x-axis, it will become 0. Okay. So kernel is this whole line. That's a geometric interpretation, and by using algebraically, then you solve that. After projection, you have x1 0, it should be 0 0. Then obviously x1 equals 0, and x2 can really be anything. And so your kernel is x2 e2, so just this line. So x1 must be equal to 0, and x2 can be anything. That's your kernel. And as we claim, this kernel is a one-dimensional subspace, so it's a subspace. Well, it's a subspace from the previous theorem, and the one-dimensional just happen to be one-dimensional. Okay. And so that's kernel, and we can also think about range. So what are all the possible things that can be that's mapped by that's the image of this L, and well, everything get projected onto x-axis. So the image, sorry, the range is the one-dimensional subspace this this x-axis, and yeah, it's spanned by E1. Okay. So it's the kernel here and the range here. Question? Yeah, both one-dimensional. Yeah. And yeah, I think later we will see that the dimensional kernel is related to dimensional range in some way. And okay, let's see another example. So our linear transformation from R3 to R2. And so you have x1, x2, x3 as input, and they map to x1 plus x2 and x2 plus x3. And once again, we see what are the kernel and what are the range and image. Do we see? Yeah. Anyway, let's see the kernel first. So kernel, whatever thing that map to 0. Okay. So this x1, x2, x3 map to this x1 plus x2, x2 plus x3, and we want it to be 0. Then we can solve for what's x1, what are possible x1, x2, x3, and so the equations here we get x1 plus x2 equals 0, and x2 plus x3 equals 0. So we have this homogeneous equation. Basically, we have a homogeneous system here, and we want to find its solution set. And anyway, so if we are doing very formal, then we can do Gaussian elimination, etc. But it's already in a very easy form, and we can just assume x3 equal to some a, and then from this equation we get x2 equal to minus a, and from here we get x1 equal to a. So yeah, so we see that kernel just always has this form a minus a with some real a, and it's just a times 1 minus 1 1, and obviously this thing is spanned by is a one-dimensional space spanned by 1 minus 1 1. Okay. Yeah. I think we can do this because write this in matrix little, because this is basically already in REF, right? So we are saying x1 plus x2 and x2 plus x3 and times x equal to 0. Okay. And yeah, so this is already in REF, so it's very easy to solve for the for the solution. Oh, where are we? Okay. And then let's see this example more. What are we? And okay, and then we want to find the image of not everything. We want to find the image of this subspace S, and the subspace S is spanned by E1 and E3. So this S is whatever A, 0, and whatever B is spanned by E1 and E3. And then we see what's the try to see what the image of it, and so we put this A0B into L, and we see it's AB, and so here is whatever AB, then obviously the image of it is everything. Okay, yeah. So so we see that the image of this subspace S is everything in R2, and obviously the range will also be everything, because you are mapping a bigger set R3. This set includes this S, so the range must also be everything. Okay, any question? Okay, and if not, then that's everything for 4.1. So we think what's the linear transformation, and we see a little bit of property, basically 0 go to 0 and minus v go to minus L of v. And now we see the kernel and the image. So kernel is whatever maps to 0, and well, image is the image. Image of a subspace is what is mapped from this S. And we see the kernel and the image are based subspaces. Okay, then let's go to a bit more technical section. That's the matrix representation. So as we said, so let's focus on Rn to Rn first. So every n by n matrix will define a linear transformation from Rn to Rn. And so I define this way: you map from x, n-dimensional x to m-dimensional n, m-dimensional vector a of x. So you just multiply this a on your x, and because the matrix multiplication is linear, so this is a linear transformation. Okay, and now we see that we get kind of a reverse of this statement, and we say that actually every linear transformation can be written as a matrix A. Okay, so yeah, so you have any linear transformation that map x in Rn to some vector in Rn, then it can be written as Ax for some. So I should probably say A sub L here. Okay, is may A obviously depends on L, so it's A sub L here. Okay. Oh, sorry. And yeah, so this is our theorem. Every linear transformation is related to a matrix A, such that L linear transform of A is linear transformation of X is just you multiply A on your X. Okay, and so here this part is already a theorem, and but the theorem actually get kind of the proof. And we also say how you find this A. Okay, so this is a very constructive theorem. And how you find the A is you can write A as columns, and actually every column of A is just whatever the basis elements of L got mapped into. Okay. So once again, here let's draw a big picture. So here we are thinking A as columns, so we have this A1 and A1 column, A2 column, A3 column, da da da. Okay, all the way to AN column. Okay, and we don't know how to write both faces, so assume those are all both faces, so those are column vectors. Okay. So yeah. So those are the AJ, and they are just whatever L map the EJ into. So remember, EJ is this standard basis element. It's 0, 0, 0, 0, 1, 0, dot, dot, dot. And this is EJ equal to this thing, and the J's element is 1. And all other thing is 0. And so let's write down the matrix a little more. So we think about yeah. Okay. And yeah. So once again here. So for example, this thing will be so for example, this thing will be A2. This is the A2 vector. Okay. Yeah, and as we say, all those AJ is defined by this linear transformation, so you just put into the first standard basis into L, and they output something, and they call that A1, and you put it into a second one and give you A2, etc. And obviously, you can list all those vectors together to form a matrix. Okay. And okay. And so we define A, and now we want to see this AX is really what we expect it to do. Yeah. And so this AX is really L of X. I want to show that. Yeah. And the proof is actually very straightforward. So we already know how the basis element get mapped. They get mapped to those A. And we just noticed that every vector x can be written as a linear combination of basis elements. And because L respects the linear transformation, and the result will be Ax. Okay, so the C is a little slower. So your x can be written as a linear combination of bases. And L is linear, so L respects this linear combination. So it becomes a linear combination of L of all those bases. Okay. So x1 of L of E1, x2 of L of E2, Okay. So now we see that we don't need to know what the L map on everything. We only need to know what L mapping those basis elements, and that already determine what the what L will do on everything because of the linearity. Okay. So well, L mapping on those linear elements. Those are those column vectors that we pick out. So those are A1 column, A2 column to AN column. And then now we just reorder things. And we see that this linear combination is like you do this matrix multiplication. It's like you this A1 column, A2 column to AN column, and you do matrix multiplication with this x1 to xn column vector. And yeah, this is exactly a matrix multiplication. And so I guess another way to see this is we see that we remember that A times X is a linear combination of columns of A. And so that's exactly this linear combination of columns of A. Okay. So we see that, yeah, you can kind of see this once again. Yeah. Yeah, AX is a linear combination of columns of A, so it's a linear combination of A1 to AN. And so we have all those equations signed together. We see that L of X equal to A of X. And we didn't restrict X at all. X is whatever thing, and so this is really true for every X. Okay, so that's a proof. Let's see. And I think here this important concept is your linear transformation is determined by what your basis element get mapped into, and we'll see different concept of this. This whole section we will try to map the different bases to different coordinates, etc. Okay. Anyway, once again, you find A by this matrix, and with every column being the linear transformation of every basis element. Okay. And we give it A and A is a standard matrix representation of L. And yeah, so we have the representation, and so representation usually means a matrix. Okay. Representation means you have some kind of maybe abstract linear operation, maybe abstract algebraic concept, and you relate as a matrix, then it's called a representation. Okay. And so this is a standard matrix representation of our linear transformation L. Okay, question? If not, let's see a few more concrete examples. So our R3 to R2, and we define, actually we have seen this before, right? So we have a 3-dimensional, 2-dimension, and defined by first one is x1 plus 2 and x2 plus x3. And we can find L of x equal to x. Oh, actually we already found this. But anyway, so we do this slower. L of x equal to x, and so the input has 3 dimensions, x1 is to x3, so we should have 3 columns, a1 into a3. And a1 is L of e1, and L of 1, 0, 0, and only have x1 here, so and so there should be 1 plus 0, those x1 plus x2, and x2 plus x3, those 2, and it's 1, 0. Then a2 is L of e2, so L of 0, 1, 0. And so 0 plus 1 equal to 1 here, and 1 plus 0 equal to 1 here. Finally, L of E3 is L of 0, 0, 1, and so 0 plus 0 equal to 0, and 0 plus 1 equal to 1. Okay, and yeah, we have seen this matrix before, so we put everything together. A equal to A1, A2, A3, and it's 1, 0, 1, 1, 0, 1 as we found, and this is our matrix A. And we check that this actually do what we think it do. So A of A times X is 1, 1, 0, 0, 1, 1 times X1, X2, X3. And so first row will become X 1 times X1 plus 1 times X2. And the second column second row become 1 times X2 plus 1 times X3. So this is X1 plus 2, X2 plus X3 as we expected. Okay, any question? Not? Then yeah, let's go over the example slowly. And so now we go to another L. L is R2 to R2, and it's rotation by angle theta in counterclockwise direction. And so it kind of feel like this. So 1, 0 rotate to here, and 0, 1 rotate to here, etc. So rotate by angle theta. Okay. And yeah, so we think AO equal to some AX. And so A1 is L of E1. And so it's easier to see from the picture because we talk about rotation in theta. So we have two standard basis element, 1, 0, and 0, 1. And 1, 0 rotate by theta go here, and by geometry we see this is cosine theta and sine theta. So this length here is cosine theta and this is sine theta because this length is 1. And similarly 0, 1 get rotated here, and so the x-axis is this line and it's minus sine theta, sine like this. And y-axis is this one and it's cosine theta. Okay. So minus sine theta, cosine theta, and cosine theta, sine theta. And yeah, so A1 as we say should be cosine theta, sine theta, and A2 should be minus sine theta, cosine theta. And we listen together and we see this rotation matrix, which you might want to see. We're probably going to see them a lot more, and you should see them a lot in every all sort of application. And anyway, this is the matrix for rotation. So cosine theta, sine theta, minus sine theta, cosine theta. And now you need to believe yourself. If you believe what we have derived, then we think that every x multiplied by this cosine theta, sine theta, minus sine theta, cosine theta matrix, you rotate to this rotated by angle theta. Okay, and yeah, so that's some example of linear transformation on Euclidean space. Any question? If not, then we'll go to harder concept. Okay, so yeah, we have more generalization. What are we generalizing to? We are generalizing into abstract vector spaces. So we have been talking about linear transformation from Rn to Rn. Okay, so those are very concrete vector spaces, spaces for your n-dimensional vectors. Okay, and n-dimensional or m-dimensional column vectors. But what about we have a linear transformation from n-dimensional vector space to m-dimensional vector space? And we found out that we can still find a matrix. Yeah, we can still find a matrix representing our linear transformation. But it will depend on basis you choose for the vector spaces. Okay. And yeah. So if you have whatever n-dimensional vector space, usually you it's not like Rn. So Rn and Rn you have a very standard basis. Is the standard basis vectors. This E1, E2, etc. But n-dimensional you have whatever n-dimensional space, then the basis is kind of whatever. At least that's what we think for now. Okay, so you have whatever basis v1 to vn, and yeah, and so that's the starting space and the end space. So the space V has n basis, and the space W has okay, yeah. So the V has n basis vectors, and W has n basis vectors. Yeah. Okay, and if we have the basis vector, then we can do similar thing before to write down a matrix. Yeah. Okay, so we have a linear transformation from V to W. Okay, and yeah. And we'll just write is ax equal to okay, so let's see how this works. So yeah, so we have a basis in V and a basis in W. So every if we have this, then we can basically map to Rn because we have the basis. Then everything inside this big V can be written as a linear combination of those basis elements small v1 to small vn, right? So you have a coordinate vector x1, x2 to xn. Yeah. Here, I think I should highlight here. Yeah. So here the thing is you have the arbitrary vector space, but when you have a basis, then it behaves really like Rn, because you can think about coordinate against these bases. So x1, x2 to xn, and similarly, you map this v to something inside w, and so that's LOV, and it has another coordinate vector according to those w. So this y1, y2 to yn. Okay. So remember, hopefully you still remember that the basis has two properties. So basis saying that it span everything, so everything can be written inside this space, can be written as a linear combination of basis element, and also bases are linear independent. So this linear combination is unique. Okay. So you have this unique linear combinations that are coordinate x1 to xn, and you map something. So this V has this unique coordination x1 to xn, and then you get linear transform into something LOV, and this LOV also has unique coordination y1, y2 to yn. And finally, then we can say about a matrix. So a matrix will relate this x1 to xn vector and this y1 to yn vector. And yeah, so it's like before, you can find a matrix A such that y equal to ax. Okay, so this is quite mouthful. Any question? Yeah, and yeah, so and this is how we represent our linear transformation as a matrix. So we have the coordination against these order bases and coordination against these order bases, and we find out that the coordination is related by A is equal to Y. Yeah. And yeah, as we said, Y equal to coordination of this LV and equal to Ax. Okay, and then once we have this, then how do we determine A is just like before. Yeah. Is yeah. So this x1 to xn and y1 to yn are basically vectors in Rn, and so how we find A is the same. Okay, and okay. And yeah, so then we also write so as before, we write A as those column vectors, and the jth column vector will just be the the coordination of this Okay, so this is multiple. So the jth element is corresponding to mapping the jth basis element of L, and then you want to write in numbers, so you write in coordination of this W basis. Yeah. So remember you have those element V1, V2 to Vn, and so basically once again you check out what LV1, LV2 to LVN are, and so there are some try to do something. Okay. Yeah. So you have those kind of think about V here, right? You have V here, and you have those bases, whatever V1, V2, V3, da da da. And then you can map by L and in W, and you have LV1, LV2, equal to whatever, we don't really know. LV3, da da da. And yeah, and you want to write those in terms of the coordination of F, and so there are some W space, sorry, some W bases that you can write the coordination down. Okay, and yeah. So if you write this in a lot of algebra, is like this. So we have the J spaces in V can be written as a linear combination of basis elements of W1 to Wn, and the coefficient we just given a name. So this is A1J, A2J, A2AMJ. And your matrix A is you just listing those column vectors together. So A1 column, A2 column to AN column. And okay, so let's see this actually works. So now we know how all the basis elements got mapped. Okay, so V1 will get mapped to so basically V1 will get mapped to this A1 vector, and A2 will get mapped to this A2 vector. That's and etc. Okay, that's a little imprecise. So V1 will get to map to a vector that has coordination A1, and V2 will get mapped to a vector with coordinate A2, etc. And anyway, and then we back to the centric. So we say what? So we know how the basis elements are getting mapped, and now back to check how other vectors are getting mapped, and once again with linearity. So we say every vector inside V is a linear combination of this basis. So you have this coordination x1, x2 to xn, and okay, so L of V is L of this linear combination, and too many of them. So let's use a more efficient notation. So it's summation. So yeah, so we write this sum into a little more complex notation. So it's a summation 1 to n, and x, so the j from 1 to n. So j is some dummy variable, and xj, vj. Okay. So j equal 1 is x1 v1, and j equal 2 is x2 v2, etc. So j equal n equal to xn vn. Okay. So this thing is, so first, so the second equal sign is just we rewrite the summation into another notation. Okay. And then the next equal sign we use a linearity of L. Okay. So we have the linear combination of Vj, and because L is a linear transformation, you can take the linear combination outside. Okay. So yeah, so you can take a summation outside, and then you can take a coefficient outside because L is linear. And okay, and then we break things again. So L of Vj, we can write it as a coordinate in terms of, so we can kind of write it as a linear combination of W, and we know the coefficients because we found that they are those Aij here. Okay. So L of Vj, as we written here, is this thing and this thing written as a complex summation is summation. Now we need to be a little careful. So now we have summation I. So we are summing over the first index of A. So summation I from 1 to n. So this is 1 to n. So Aij and Wi. Okay. And Wi are vector. Okay. And so we see that this is double summation of those Wi. And but anyway, we care about the coordination in terms of Wi. So what are the coordinate to some I, and so we swap the ordering of summation, and so the summation I go to outside, and we see what the summation j is. So we just group terms together. So sum j, and we have aj and aij here. So sum j, aij, xj, and wi. Okay. And so our algebra tells us that LOV is this. I forgot to boldface here. Anyway, okay. So LOV is the summation of basis vector times coefficient. That's sum j, aij, xj. Okay. And then we can just think about what's aij, xj, and well, aij, xj is really so we think about x vector here, and let's see, or maybe this is better. Okay, so aij, xj is really doing matrix multiplication, because you can think about your matrix A and your vector x1, x2, to xn, right? So you have the input. Handwriting is not very good. So some aij, xj. So you have this A here, and you have this vector x here, x1, x2 to xj, and so j is getting sum over, and we have some I here. So some I correspond to wi, I here, and then you have a I1, a I2, to a I. I should not say j here. Is a I n here, and this is xn. Okay, x1, x2 to xn here, and a1, a2 to an here. And yeah, so you see this summation is really this matrix communication of I0 and this column vector, and this will be the ith coordinate of the output vector. Okay, so you think about the matrix A times your vector x, and the ith vector. So this ith component of the output will be this sum aij, xj. Yeah. And yeah, here we write this funny notation. So this and yeah, so we also think of this as the inner product of the I0 with your x vector. Okay. So we have this funny notation to mean the I0 of A. So I0 of A inner product with you, or multiply with your x vector, and and it will be the ith element of the output. Okay. And yeah. So we see that this is what we expect. So the output vector the ith element is this, and then every element will just be. So this whole output vector, this coordination. So notice so this thing should be the yi. So the ith coordinate of the output vector. Okay. So we see that y, so yi is this I of x, then this whole vector y should really be just this whole ax vector. Okay. And yeah, so this is complete the proof. We prove that the output coordinate, the output has coordinate vector that equal to ax. Okay. I think this is a lot of notation, but really we are not doing anything new. We're just making notation a lot more complicated. What do we do? The important thing here is you want to find a matrix, then you find out what are the linear transformation of the basis elements, basis vectors. So you put your n basis vector into your linear transformation, and you get all n vectors into your output space W. And now because we want to find coordination, then we just find the coordinate of all the output vectors. Then you list them together, and you see that because you know all the linear transformation of the basis, then you also know the linear transformation of everything else, because everything else is a linear combination of your basis. And so when you do linear transform, then that's just a linear transformation of just a linear combination of this linear transformation of basis. Okay. And then you group things together, and you see your y equal to ax satisfied. Okay. And okay, I guess we can finish this now. Okay. So write this out as a theorem. And so we have two vector space that we have found the order basis v1 to vn and w1 to wn. And then there is a corresponding linear, so every linear transformation there is correspond to a matrix. Okay. And the matrix will tell you how so a starting vector has a coordinate. So the starting vector v is a coordinate in terms of e, and we will get linear transformate by L. So this is v linear transformation by L, and they go to this space W, and the coordinate in terms of f is equal to your matrix A times the coordination in terms of basis E. Okay, so this is quite a mouthful, so but you need to read this carefully. And so here this square bracket f we means coordination in terms of f. So this is the m-dimensional vector, and this square bracket e means coordinate in terms of the basis e, and so this is the n-dimensional vector. So n-dimensional vector times your m times n-dimensional matrix A becomes the m-dimensional vector. Okay. And yeah, and we call this A a matrix representation of L relative to the order basis E and F. So basically this A is a matrix, so it's called a matrix, and it's relating to L, so representing L. And but the form of A depends on how you choose E and F, and so it's relative to the basis E and F. Okay. And from our statement before, we have our statement here we have found actually I guess we are doing the proof of the theorem before we state the theorem. But proof here we have control how you find A, and we say you find the jth column of A by just having the jth basis element of V and going through L, and then you just find a coordinate in terms of F. Okay. And so here is some picture that make things we say a little more clear. So think about there is a vector space V and W, And there's a linear transformation from V to W, so this line L. And we found out that we can use those coordinates. You can use the coordinate to transform between basically your V and Rn and W and Rn, because there is a unique one-to-one correspondence between the coordination vector and the vector in V and the coordinate vector and the vector in W. So you can use a coordinate, you fix the basis, and you have this one-to-one correspondence between Rnv and Rnw. And then Rn to Rn, you have the transformation A. And we found out this A corresponds to your L. Okay. And so this is 1-to-1, 1-to-1. So you got made by A, if only if you get made by L here. Okay, so I think it's easy time to take a break. So let's take a break and go back 10 minutes later. Okay. Hello. Hello. Wait. Hello. Okay. Yeah. Okay, let's get back. Yeah. So we have been talking about the matrix representation of linear transformation. And yeah, so here is, I guess, the simplest possible representation theory. So let's go a little digress. So there's a whole bunch of a very big theory in algebra is how you write down abstract algebraic concepts in terms of matrices and vectors. And so here we have seen a very simple example of a representation theory where we say we have whatever vector space V and whatever vector space W. Well, not really whatever, they are finite dimensional vector space. So yeah, we have a finite dimensional vector space V and a finite dimensional vector space W. And we also have a linear transformation between them. And we can map V to map vectors in V to vectors in Rn by having by fixing some basis E here. Okay. So there is E here, E equal to V1 to Vn, and we have F here equal to W1 to Wn. Okay, that's maybe I guess let's keep doing this. Yeah. Yeah. So you have fixed on order basis V, E, and F inside V and W. Then we can have this representation of vectors inside V and representation of vector inside W. And then we'll have a corresponding representation of this linear transformation L to matrix A, because we know every linear transformation between Rn and Rn is can be written as a matrix. And so once again, for example, we find the columns of A by having that if we have Ej here, and you will get mapped to this Aj, so the jth column of A. Okay. And then the Ej corresponding to Vj here, and Vj get mapped to some L of Vj. Okay, and yeah, and so what we do is we have Vj here. Okay. Let's hope this is not too complicated. So Vj is having some correspondence with Ej, and yeah. And then because we have this, and then we know we also have these two should correspond to each other, and yeah. And so we can find Aj by having so we from this dotted line we know that Aj equal to the L of Vj and mapped by F, coordinated by F. Okay, so this is the high level idea of what we do. We want to find Ej. We might want to find for every Ej maybe to some Aj inside is Rn to Rn. So you can go back, and the Ej corresponds to Vj, and the Vj to get made to L by Vj. And the thing here and the thing here, they are related by this F. So this Aj should be LVJ's coordinate. Okay? Hopefully this gives you more intuition about what we were doing through all this algebra. Okay. Now have this abstract picture. Okay, and to create things a little less abstract, let's see once again more examples. And okay, but we're being a bit funny. So we have an example. So we're talking about this V and W very abstract. but we can also have V and W being, this is a bit confusing, but we have V and W also being R and Rm, but we just pick different bases of them, okay? And, okay, so let's see what we are doing. So what we are doing is we think about some mapping. Okay. Okay. So let's see what we're doing. We are doing from R3 to R2, and R3 to R2, and we can define our linear transformation like this. So R3 has x1, x2, x3, and it map to R2. And so this mapping into R2, we write it in a funny way. We write it as x1 to some b1 and x2, x3 to some x2 plus x3 times some b2. And we have b1, b2 here. Okay. And so why we want to write this is we want to write our v is just R3, but our w is R2 with funny basis b1, b2. Okay. So here is we're doing a really funny example. Okay. But here is we're rewriting this W not in standard basis but in this basis B1, B2. Okay. And okay, so we want to find a matrix representing L that map from basis E1, E2, E3 of R3 to basis B1, B2 of R2. Okay, so yeah. This is what I can do because, as we say, those things those things depend on the basis you're choosing for your V and W. So obviously we can do really stupid things as not really stupid but a bit funny thing. That you choose your V and W just being R and Rm but have different bases, order bases E and F here. So in this example, I think we have E equal to standard basis, so V is really just Rn, but F we change to some basis B1, B2 here. Okay, so that's what we are doing. And anyway, so we can do solution, and as we say, we do this solution, and we want to find L of the basis you are making here. And it's the same basis, so L of E1, E2, E3. And we want to find the output in terms of B1 and B2, and we have a nice form of L given here. So it's already in a linear combination of B1 and B2. So L of E1, and you just read out the formula, then it's 1B1 plus 0B2. Yeah. And L of E2, 0B1 plus 1B2, L of E3, 0B1 plus 1B2. And so now we will write this thing in terms of coordinate, in terms of, we think of this as coordinate in terms of B1 and B2, then obviously the coordinate will be this 1, 0, and this is 0, 1, 0, 1, and this is 0, 1. Okay. And yeah, so our A, by our formula, should be L of E1 in terms of F, then L over E2 in terms of F, then L over E3 in terms of F. So A is this thing. Okay. Okay. And yeah, so this thing is this, and I guess we can try so let's try if we have instead of B1, B2, we have E1, E2, E1, E2 here. Let's just do a little comparison. So you have E1, E2 here, and so we write this out. So we have L of X equal to X1 times 1, 1 plus X2 plus X3 times minus 1, 1, and this should be x1 minus x2 minus x3, and x1 plus x2 plus x3, right? and so we write this as a matrix. So A sub standard basis will be 1 1 from the x1 and minus 1 1 from the x2 and minus 1 1 from the x3. And you see that this is a different A than this A here. Okay. So this A depends on the basis you choose here, as you expected. Okay, and let's see another example. Okay, and okay, okay, and here we have R2 to R2, and now we change both the starting and the end basis. As this is a bit funny. We change both the starting and the end basis with this B1, B2. Okay. So we use this B1, B2 twice. Okay. And so B1, B2 is this thing here, but with the form we write here, we really don't care about B1, B2 as you will see soon. Yeah. So we think about L will map whatever linear combination of B1, B2 to this linear combination of B1, B2. So we kind of think, okay, so here we have funny things. So we have this E equal to B1, B2 and F equal to B1, B2. And so we have R2 here, and they are related to R2 and R2 here by this transformation by B1, B2, both of them. And anyway, but we are given L in terms of B1, B2 on both sides. Yeah. And so AO maps this alpha beta coordination vector to alpha plus beta and to beta. And so we want to find then we want to find the matrix A with respect to B1, B2 on both input and output. And this is just a really complicated notation to get you a bit more familiar with the abstract concepts, but the calculation is very easy because it's basically just alpha beta and 2 beta, alpha plus beta and 2 beta. And but anyway, let's go through this carefully. So L, so we map the first basis element of the input V into a basic vector. Okay, so let's write down the things here. So so we have V to W, right? So V to W, and V has basis B1, B2, and W also has basis B1, B2. So it's a little confusing here. Okay, but anyway, we want to map this B1, B2. So we want to find where this B1 and this B2 get mapped into. Okay, so the first basis of V is B1, and as we see here, it should get mapped to, and there is a 1 B1 plus 0 B2, and so it should get mapped into 1 plus 0 B1 and 2 times 0 B2. Excuse me. And yeah, so that's 1 B1 plus 0 B2, and so the coordinate in terms of B1, B2 on this W is 1 and 0. Yeah. And so we know the first column of A is 1 and 0. And similarly, you map this B2 to something. Okay. And B2 you can write as a linear combination of B1, B2 with alpha, beta, alpha is equal to 0, 1. And so it maps to 0 plus 1 B1, and so beta equal to 1, and 0 plus 1 equal to 1, and 2 times 1 equal to 2. So that's a 1 B1 plus 2 B2, and so this is already in the form of a linear combination of B1, B2, and so we see the coordinate here is this 1, 2 here. So the second column is 1, 2, and your A is 1, 0, 1, 2. Okay, so the calculation is really easy here, but it just show you the abstract concept of this mapping between vector spaces with some ordered basis. Okay, question about this example. Otherwise, let's see theorem. Okay. So the theorem that basically generalize what what we were doing in the previous example. Okay, so we have our vector space being R and Rn, but with some funny order bases that are not standard bases. So you have a basis is E equal to U1 to Un, and okay, we change some name for reasons. Okay, so E equal to U1 to Un, and F equal to B1 to Bm. So E is the basis for Rn, and F is the basis for Rn. And so we want to find, so we have a linear transformation from Rn to Rn, and we want the matrix A representing this L with respect to E and F, and then once again we will find the columns of A, and you can find it by mapping those basis elements with L by L, like we said before, and we want to find the basis element with respect. Sorry, we want to find the coordinate with respect to F, but F is the basis for Rn. So now we can just use structure of Rn, and now we have something a little different. That is, we have this -1. Okay. And we recall from chapter 3 before that we can change between coordinate. Now this is how you change the coordinate with respect different bases in Rn, right? So this L of Uj, we write this as coordinate. So this is so this part we are thinking it as not. Oh, sorry. Okay, so it's a bit confusing, but this part we are thinking it as not really abstract. We are thinking it is as coordinate in terms of standard basis. Okay. Oh wait. Spelling is wrong. So this L over Uj is coordinate in standard basis, and we change it to coordinate in F by applying this B-1 vector, where B is the matrix as you just listing all those things together. Because remember we say we want to change from coordinate from F to standard basis, then you just multiply by this matrix, and then you want to do the inverse transform of the coordination, then you apply this inverse matrix. So this LUJ is coordinate in the EJ. Okay. So yeah. So you do this transformation of coordinate, then you can find your the coordinate in your chosen basis, and then you can apply previous theorem. You have the matrix. You list your matrix as you list as columns of coordinate, and you will get your matrix A. Okay. And yeah, so we kind of already give you a high level proof, but let's see a proof in ugly details. Okay. So let's see the proof in algebra. So we have some A representing L, and with respect to our basis E and F, so the coordinate E and F. Okay. And yeah, and then LUJ. Okay. So what do we do here? We say, okay, so we want to find yeah. So we want to find what L map the basis element into, and we say it's is whatever thing. L of Uj is something. So and it's also a linear combination. So it has, why do we have minus sign? I don't think we have minus sign here. Sorry, we have a typo here. Okay. Okay. And yeah, so it's linear combination A1J to A2J to AMJ of your Bn. Okay. And so remember this coefficient is what we want because we list them together and they will become a vector. It should become the jth vector of our matrix A. Okay, but anyway, and we can rewrite this together in this form. We rethink this as a linear combination of B's. So we can think B. We can write those B in standard basis and list them together as a matrix. This is our matrix B, big B, right? So B1 in B1 is a vector in Rm and it has its coordinate in standard basis. So it's B1 vector and same B2 to Bn. And it's a linear combination of them. We can think about linear combination of column vectors as a matrix. This column listing together times vector A1J to AMJ. And yeah, so we see that this B matrix times AJ and times this AJ vector. And yeah, so this A1J to AMJ as we said, this is the AJ vector we want to find. So this is B times AJ. Okay, so those are all equal sign together. So we see the L of Uj in standard basis. Okay, is this B's in standard basis. This thing as a matrix times the vector we want to find is AJ. And yeah, then because B is the basis, it has the inverse. Then we just multiply B inverse on both sides. So B inverse times B equal to 1, so we get AJ here. And on left hand side become right hand side is B inverse L of Uj. Yeah, on high level we are just doing this change of basis. So we were writing L of Uj in standard basis and we want to change it into the basis of this B and so we apply B inverse. Okay? Any question? Okay, so maybe let's see an example. Okay, so in this example, we actually need to do all the change of basis. Okay, this can take quite a few times. Okay, so we have R2 to R3. Okay, so now it's harder. The previous example, we already given our linear transformation in terms of the weird basis. But now in this example, we are given our linear transformation in terms of standard basis. Okay, so this is in a form that we have seen quite a few times before. So you have R2, so you have some x1, x2, and then you change to R3 and equal to these three linear terms. So x2 and x1 plus x2 and x1 minus x2. Okay, and yeah, so from here you can read the matrix in standard basis is easy, but we want to matrix in our weird basis. So we have some basis U1, U2 for your our R2, and some basis B1, B2, B3 for our R3. Okay. And they are given here. So U1 is 1, 2, U3, U2 is 3, 1. And B1 equal to 1, 0, 0. Okay, it's standard, but then B2 equal to 1, 1, 0, and B2, 3 equal to 1, 1, 1. Okay. And yeah. Okay. And so we want to find our matrix with respect to U and B. And as we said, the first thing we want to find is we want to find the linear transformation of the basis from the starting space. Okay, so from the L of U1 and L of U2 first, and it will be standard basis. So L of U1, so it's 1, 2. And let's do this slowly. So first one is x2, so it's 2, so it's 2. Then x1 plus x2, so 1 plus 2 equals 3. And x1 minus x2, so 1 minus 2 equals to minus 1. So U1 got mapped to this 2, 3, minus 1 is in standard basis. And U2 got mapped to yeah yeah U2 got mapped to, so U2 is 3, 1, and so it got mapped to x2 equal to this 1, so it's 1, and x1 plus x2, so 1 plus 3 equal to 4, and x1 minus x2, so 3 minus 1 equal to 2. So L of U1 and L of U2 in standard basis is what I found. Now we want to find this as a linear combination of B1, B2, B3, and this as a linear combination of B1, B2, B3. And so we can apply B minus 1. So we want to apply B minus 1 on both of them. And there is, okay, so let's write B first. Actually, no, let's just go to the next page. Okay. And so B is this matrix 1, 0, 0, 1, 1, 0, and 1, 1, 1. And the two vectors we found here, so 2, 3, minus 1, and 1, 4, 2. Okay. So this is L of U1 and L of U2. And we want to apply B minus 1 on that. Okay. So obviously you can do the thing we know before and find the B minus 1. But there is a bit faster way to do this, because remember you can do this is a generalization of how we find B, one of the generalization of how we found B minus 1, right? So we had before that, you want to find B minus 1, then we can have like a B and identity matrix here, then you do row operations, and you become identity here and B minus 1. Okay. And here is similar, so you're thinking about you also doing the row operation, and because the row operation is reversible, so whenever you turn this B equal to identity here, and you will actually just be multiplying B minus 1 or whatever on the other side. Okay. So you can have pretty a bit faster way to apply B minus 1 on both those vectors. That is, you write B here and those two vectors here, and you do Gauss-Jordan elimination and turn this one side into REF, and this become E minus 1, and you do all the row operation on those vectors correspondingly, and this will be the B minus 1 of L of U1, and this will be the B minus 1 of L of U2. So skip the middle calculation. But obviously you can also find B minus 1 and do matrix multiplication. It will be just, you just need to do one more matrix multiplication. Okay? And yeah, so you do Gaussian elimination here, and you have to do a lot of practice on this, and you get your A equal to this minus 1, 4, minus 1, and minus 3, 2, 2. Okay. And yeah, and hopefully we can verify that this is true. L of U1 equal to minus B1. Let's see, we have a lot of time, so maybe let's do this. Why not? Okay. Yeah. So minus 1 times B, minus 1 B1, and 4 times B2, and minus 1 times B3. Okay. So this thing is equal to so this one equal to minus B1, so minus 1, 0, 0, plus 4B2, so that's 4, 4, 0, and minus B3, so minus 1, minus 1, minus 1, and this equal to, so minus 1, 4, minus 1 is 2, and it's not too interesting, but okay. And then the middle one, and 0 plus 4 minus 1, so 3, and 0, 0, minus 1, so it's minus 1. So 2, 3, minus 1, as we say here. And the minus 3, 2, 2 times our thing. So that's minus 3, 0, 0 plus 2, 2, 0 and plus 2, 2, 2 and so minus 3 plus 2 plus 2 equal to 1 and 0 plus 2 plus 2 equal to 4 and 0 plus 0 plus 2 equal to 2. Okay, so we check if our answer is correct by the middle one. Yeah, we need to check the Gaussian elimination. You need to do the Gaussian elimination. But this is already in row echelon form, so it's easy. You subtract those two out, and then you subtract this one out. Yeah. So any question about this example? So because this is a very detailed example, so you see both you have a basis on the starting, you have a basis on the starting space and a basis on the end space, and you see how every calculation, what you need to do. Except we skip the Gauss-Jordan elimination part, which you have a lot of practice already. Okay. And okay, so we have our checklist for 4.2. I think we'll end early today. There is a little bit on 4.3, but we can leave that for Wednesday. Okay, so let's finish the checklist of 4.2 and stop early today. So yeah, here are theorems in 4.2. But anyway, basically what we are thinking in 4.2 is we want to find the matrix representation of our linear transformation. So we start with our vector space being nice. So we transform from Rn to Rn. Okay, so we have some Rn to Rn. And we found out that for the transformation in Rn to Rn, and if you think about both R and Rn in standard basis, E1 to En and E1 to En, then you can easily find your matrix representation of x equal to x with, so the jth column of A is just linear transformation of the jth basis element of your input space. Okay. So this is a recurring thing, so we keep trying to find the linear transformation of the basis element of the input space. Okay. So this is 4.2.1 and it's from Rn to Rn, and then we have our very generic generalization of finding a matrix representation of every L between every abstract vector space V and W. So we have whatever V to whatever W, but V has dimension n and W have dimension n. And we say that we can have one-to-one correspondence between V and Rn if you fix the basis on V, and also you have one correspondence between W and Rn if you fix the basis in W. Okay. So you have the basis V1 to Vn and the basis W1 to Wn. And this one-to-one correspondence is whatever vector in V you have a unique coordinate, which is n real numbers, and so that's a vector in Rn. And also in W, then you have a coordinate in terms of this W1 to Wn unique coordinate, and a unique coordinate we think it as a color vector in Rn. Okay. And then finally, how you find the matrix representation is you have this one-to-one correspondence. So you have a coordinates map to you go to this Rn to Rn and Rn, and you find a matrix representation. Sorry, a matrix that correspond to how the coordinates change from Rn to Rn. Okay. And yeah, as we say, we want to find how the basis vector get mapped. Okay, yeah, so that's this block we are talking about. So we are thinking the coordinate of whatever vector V. So you have V So start here. So whatever vector v here, and you go to x here, so it has a coordinate. So you go to Rn here, it has coordinate, and so the coordinate will map to here to something, some coordinate. Okay. And that coordinate will correspond to coordinate of you have the v starting here, you get to LOV here. Okay. So you have v star here, you get to LOV here, and that LOV will have the coordinate that's a times the coordinate here. Okay, and yeah, so that's the most general example. And once again, yeah, so we want this to happen, and it's a bit circular, but actually it's well defined. And you can find this AJ by knowing this is true. So AJ, you can find, once again, you can find this A by reading the columns of it. So, and you go to the down space here, and you want to find the columns of AJ, and you find out the AJ corresponding to the J's vector. J spaces vector got made into. So you have a J spaces vector here, and then you map it into this W here, and then you find the coordinate here, and that's your AJ. Because that corresponds to you map the standard basis here to here. And then, okay, so 4.2 is actually the most general thing, but then we specialize it a little bit to B and W being R and R, and okay, but this is still a little different from 4.2.1 because we change the basis. Okay. So we still have V and W equal to R to R, but with whatever different basis, U1 and B1 to Bn. Okay. And yeah, and this matrix representation thing is really the same. But now we are in Rn, and we have this really complete expression for the basis E and F. So basically you have the E and F in terms of standard basis. And so we have a closed form formula for our AJ here. Okay. So this AJ, so we can basically solve this L of Vj in coordinate F. Okay. So all of Vj. So Vj is just Uj here, we change the name for whatever reason. Okay. So L of Vj is just L of Uj. And but the actual thing we do here is finding coordination F is something already done before. Is a change of coordinate between standard basis and your basis F. And that's just done by multiplying B minus 1. And I have seen in this example that how all of these things work out. So over U, you just do whatever this form value is given you. And then in B minus 1, we see that we actually have a bit of faster calculation. So, so yeah, so you can do the B minus 1 on vectors by doing these augmented matrix and row operations. Okay, so I think we have 10 minutes extra. It's probably a bit short for 4.3. So this is probably enough for today. So we'll stop here and let's see you on Wednesday. Wednesday not too sure. We'll probably talk a bit about midterm and hopefully maybe we'll finish 4.3. We're pretty ahead of schedule, so let's take it easy. Okay, so yeah, see you on Wednesday.